In the 1970s, Stephen Hawking presented one of the biggest puzzles in modern physics, the information paradox. Hawking claimed relativity ensures information is destroyed in black holes, but this allegedly violates quantum mechanics. So many physicists think black holes do preserve information. In this film, we'll hear from some of the giants of relativity who claim the physics community has it wrong. They say information loss is nothing to worry about. Roger Penrose argues that quantum mechanics must be modified, while Bob Wald and Bill Unruh suggest information loss doesn't violate quantum mechanics. What they all agree on is that Hawking was wrong to change his mind.
I remember boarding the plane to go to the GR17 conference in Dublin, and Stephen was on the plane as well, which surprised me, not because Stephen was there, but because his name wasn't on the delegation list.
Yes, this was a conference in Dublin, which Stephen was not originally invited to, but then he considered he'd made a great discovery and decided he wanted to come. And this caused a certain amount of havoc among the organisers because they had to redo the programme in some serious way.
On the Wednesday, which was the 21st, there were a set of plenary lectures, and I noticed Stephen's name was on there. So, of course, 2 and 2 made 4 in my book anyway, and I realised that something was going to be announced. The place was just packed to the rafters with press. So I remember a few of us being given preprints of the plenary lectures as we walked in. And we sat down. Before I had time to actually read anything, I noticed that the murmuring that was going on suddenly ceased. It was quite a shock, but these words will be indelibly etched on my memory. And he said, "I want to report that I think I've solved a major problem in theoretical physics." There was a pregnant pause, and a number of us looked around at each other, and I, for one, wondered what on earth he could be talking about. I kind of flicked into my mind that it could be some kind of weird quantum theory of gravity that didn't incorporate strings or something of that nature, but of course it wasn't. It was the fact that he was going to announce a solution to the black hole information loss paradox. His belief was that when information, so light, matter, whatever it was, got gulped up by a black hole, when it eventually evaporated via Hawking radiation, the information was essentially lost from the universe. So the black hole would explode right at the point of it disappearing, and the information then regurgitated would be mangled in a mangled form. And he believed that for many, many years. In fact, that was the basis of the bet with himself, Kip Thorne, and John Preskill. He and Kip believed that that would be the scenario. John Preskill, on the other hand, believed that information, when scooped up by the black hole, would then be retrieved again in the universe in effectively an unmangled form, so a readable form, as it were. So he believed this for many, many years, and of course, suddenly at the GR17 conference, he made this spectacular U-turn. So going from basically the relativist point of view to the quantum theorist point of view. So this was quite shocking. You could see 2 groups of people, one looking at the stage with glee, basically saying, "Oh, we're vindicated." Another group looking down at their preprints and wondering what on earth this is going to mean to theoretical physics. And Kip Thorne was invited to give his impressions of Stephen's talk. And I, for one, and I'm sure other people felt the same way, believed that Kip, like Stephen, was about to concede the bet. But no, he stuck to his guns.
One of the people that he was betting with was Kip Thorne. And Kip Thorne, I believe, didn't consider that he actually won the bet. And he wanted to think about it more, which is a quite curious reaction.
Stephen conceded, and therefore John Preskill was presented with his trophy of an encyclopedia of baseball, if I can remember rightly, which he shook triumphantly above his head as if he was a world champion boxer who just won a title.
We heard that he would be giving a talk, and then his student would be talking, answering questions and so forth. So we approached the student, and the student said to us, be be gentle with your questions, because, I'm going to have to answer the questions from people like you, and we haven't really finished the calculation yet, which I found astonishing. Here he is giving this big announcement, and he hasn't really finished the calculation yet. And, sure enough, that part of that at least came out in the talk. And then about 6 months later, I was at a conference in Cambridge, and the student gave a talk on this stuff. And one of the conclusions of his talk, not explicitly, but certainly implicitly, was that the whole calculation hadn't worked. And so I said, do you mean that you do not have a proof that of information retention, etc.? And he said, not yet. And Stephen was just sitting right beside me and didn't say a word.
It wasn't clear and cut and dry that what Stephen had done was actually solve the paradox. In fact, even to this day, so 20 years later, there's still a great deal of research being carried out on the black hole information loss paradox. And I believe also that since 2004, Kip Thorne has not conceded the bet to John Preskill.
I think that what Bob and Bill and I agree on is that the black hole information loss problem doesn't make the situation worse. Now, you may have an argument where it's saying that current theory is okay for some reason, and I think that's more the Bob and Bill viewpoint. Or you might say current theory is not okay, which is my position. But the black hole doesn't make much impact on that.
The problem is that you've got a place, inside of the black hole, where you don't look. So sitting in this room, photon leaves this room, goes out, heads off into space. I will never catch it, because I would have to go faster than light to catch up with it. I will never see it again. That information is lost, as far as I'm concerned. Does that bother us? Does that say that somehow the physics inside this room is invalid, or, that we don't know what's happening? The answer is no. We know exactly what's happening. And that's exactly what's happening in a black hole. There you have the horizon, which is a one-way membrane. You can go in, but you can't get out of it. And the information goes in there. Our best idea of what's going on in the black hole, the classical one at least, is that in the center of the black hole there's a singularity, and that singularity is where this information falls off the edge of the universe. Like Columbus was worried about sailing off the edge of the world if they went out far away from shore. This is a place where you would fall off the world. Whether or not that's actually what happens when we eventually get a quantum theory of gravity, I have no idea, because we don't have that theory yet. But whatever it is, that stuff doesn't come back. At least that's my belief. Whereas their argument goes something like, well, look, remember this black hole, you had this horizon of the black hole, stuff falls into it. But eventually that evaporates in, 10 to the 60th years or whatever, as the black hole slowly, very, very slowly evaporates. Eventually that horizon disappears. Now you've just got something that looks like flat space with matter in it. And I no longer have this unitarity, which just says that a unique event in the past produces unique events in the future. They don't like that. Okay, they want somehow, the information to be preserved, and exactly why is a bit of a mystery to me.
The behavior is not such that any observer would see a local violation of ordinary laws of physics, including all the laws of quantum physics. It's really a kind of global difference having to do with the fact that you originally had something that you can calculate the forward evolution of, but because a component of what you're evolving to has disappeared off the face of the earth or the face of the universe, or at least the part of the universe that we have access to, what you're left with is in a mixed state.
A pure state in quantum mechanics is when we exactly know what the state of the system is. So this is a precise information. It could be one electron is spin up, another electron is spin down. It could be one is spin up, this one is a spin up, this one is spin down. If you don't have access to all information, all the space, you can just see only one of these electrons. Then situation changes. Then you're not in a pure state anymore, because this electron could be a spin down and could be a spin up or spin down. So that's called a mixed state. So that means that you don't actually know, or you don't exactly know what's going on. So it's like a regular probability that we have.
The unitarity principle in quantum mechanics says that a pure state must evolve to a pure state. This ensures physics is time reversible, allowing us to infer the past and future states of a system. That is why unitarity is so fundamental. Most physicists believe information loss violates this principle. But does it?
The observers outside the black hole that are seeing the Hawking radiation, and at the end of the process, all they see is the Hawking radiation and it's in a mixed state, they're never seeing some violation of laws of physics. So I don't consider this a serious problem. Most people, most physicists, aside from Bill Unruh, Roger Penrose, and me, find that very troublesome and, find all kinds of, try to find all kinds of, in our view, strange ways of avoiding that conclusion that usually involves serious violations of ordinary quantum mechanics, as opposed to this departure from what normally happens in quantum mechanics, but is not really giving any local violations of quantum behavior.
I think that the reason people are so devoted to unitarity is just the power and incredible effect that this discovery of quantum mechanics has made on our understanding. It's basically, quantum mechanics is about small things. General relativity is about big things. Big things are made out of small things, so the theory of small things dominates. If you have a small thing and a theory about small things, then that theory, when developed enough, should describe how big things behave. So I think that's an inbuilt view that people have, which is not an unreasonable view, I would say. I just claim that it's not correct. It's not correct in the sense that gravitation theory, see people talking about quantizing gravity. That means applying the rules of quantum mechanics or unitarity, which I would say is a basis. I think the question was originally about unitarity. The unitarity, you see, is how things seem to behave if you leave them alone and if they're small enough. And if you like, it's the Schrödinger equation. The Schrödinger equation tells you, if you know what the system is like, exactly what the state of that system is, then 10 minutes from now, you can calculate what 10 minutes from now it would be like. Just apply the Schrödinger equation. It's a completely deterministic equation. It tells you how the system would evolve according to this equation. That's just an aspect of unitarity. You may be familiar with the Schrödinger's cat paradox, if you like. Schrödinger put this forward. He had a sort of experiment, a thought experiment, where you'd have a cat and you have some quantum event which then decides whether to kill the cat one way or and either by poison or by shooting it or something, or not, you see. Whether it does it or not depends on the quantum effects, and it's the collapse. Well, you see, Schrödinger was pointing this out to say that that is a prediction of his theory, if you like, the Schrödinger equation. If you follow that religiously, yes, the cat should be in a superposition of being dead and alive at the same time. Schrödinger was more or less saying, look, my theory, that's Schrödinger talking, my theory is absurd because it tells you could have a cat that was dead and alive at the same time. What a load of nonsense.
While Roger Penrose agrees information is lost, his reasons for doing so are quite different. as Penrose is challenging the very foundations of quantum mechanics.
If you try to take the view that quantum mechanics does not allow information to be lost, because the thing which is called unitarity does not allow information to be lost, if you like. But I didn't really believe in unitarity either, because in my view, this fundamental quantum mechanical process, if you like, unitarity, is basic to quantum mechanics. But the trouble with that view, in my opinion, was that quantum mechanics can't be universally correct because it does not explain the measurement process. And the measurement process is left as a puzzle, which people have half answers to, but never any proper answer to, from the point of view of standard quantum mechanics. My view that when you get gravity involved in a serious way, then the unitarity has to be violated. And I had an argument going way back to the sort of turn of the century, which I thought was a fairly strong argument to show that the general principles of general relativity, and which is the principle of equivalence, which goes back to Galileo, basically, that if you drop a big rock and a little rock from the Leaning Tower or anywhere else, if there's no atmosphere to get in the way of it, then they will drop together. So you can cancel out gravity by falling freely with gravity. Just fall freely and the gravitational force disappears. Now that is the fundamental principle that Einstein then picked up on and based his theory of general relativity on. Now the other fundamental principle is the fundamental principle of quantum mechanics, which says if some one thing A can happen and another thing B could happen, then there are combinations of A and B that can happen as well. So A plus B or A minus B or A plus square root of minus 1 times B can all exist as separate possibilities. Now you don't see any of these things in the real world, but this principle I showed in this argument is incompatible with Einstein-Galileo principle of equivalence. And so that you have to modify the principle of superposition so that it's not really a total thing. It only lasts for a length of time. And that length of time depends on gravity. And that length of time is something you can calculate. It was originally found independently of me about 2 years earlier, in fact, by a Hungarian, Lajos Diósi, and he had got the same formula. He didn't use the same argument as I had, but he had the same formula. I was not aware of this at the time, but this was sort of confirmation of that formula. Now the formula tells you that if you have a superposition, then that superposition will live for a certain length of time, which you can calculate from the gravitational interaction between the two possible locations of the body. And it's a sort of theoretical consideration. You imagine that the body was in two places, and then you work out what would be the gravitational self-energy of that superposition. Or another way of putting it is you think of that body in one location, and you imagine another copy of it on top of it, which you move to the other location. And you ask, how much energy would that cost you if you just consider gravity and no other forces? I mean, gravity is very weak compared with electricity and magnetism and nuclear forces, certainly. All these things are much, much stronger. But if you don't count any of those other forces, just gravity, then that energy is more or less what you regard. You take the inverse of that energy in sort of absolute units, and that gives you the lifetime. And that's the same formula that Diósi had come up with before. But if you take a view like this, then unitarity is not a rule which holds for all systems. It holds for a while. The smaller the system, if you like, the longer it holds for. So atoms and molecules and things, it would be longer than the age of the universe from the Big Bang to now, much longer than that time. But if you take a little pebble or stone, grain of sand or something, it would be almost instantaneous. So it depends very much on how much mass there is in the object you're thinking about. Now, this tells you that when you try to combine gravity with quantum mechanics, you have to do a modification not only of gravity, which sure I agree would happen at some level, but you would need to modify the principles of quantum mechanics, most specifically the unitarity principle, which is foundational to quantum theory. Unitarity has gone out of the window at this time. Why should we worry about unitarity for black holes? I mean, the black holes are huge objects, certainly compared with my grain of sand. You don't worry about it for the grain of sand, so why should we worry about it for a black hole?
So what Roger's saying is that unitarity is perpetually being violated every time a measurement or an observation is being made, yet quantum mechanics is still able to predict physical outcomes. Bob and Bill are saying that unitarity is not being violated, but that's only within a certain realm of validity. So both Bob and Bill and Roger agree on the loss of information in a black hole, but they disagree with the idea of unitarity either being violated or not being violated in that region.
So in this discussion, there are basically three camps. One of the camps is the string theorists and particle physicists camp, which says that if you lose information into the black hole, then for anybody outside the black hole, you basically destroy quantum mechanics. One of the key features of quantum mechanics is that unique initial conditions give you unique final conditions. And here, if you stay outside the black hole, that's no longer true. Bob and my position is that is sort of the most conservative, if you will, that ordinary quantum mechanics works perfectly well for black holes. And one simply has a situation in which there's some area which you cannot, in principle, look at because of the horizon of the black hole. In quantum mechanics, ordinary quantum mechanics, if you have something that you cannot look at, then that automatically leads to loss of unitarity and loss and information loss, because the information is in that region where you don't look at it. Roger's position is that gravity should, in and of itself, lead to a loss of unitarity, that the energy in the gravitational field of whatever system you have itself creates this loss of unitarity, even if you can look everywhere. So even if you do a tabletop experiment, which is in your lab, and you can look at every bit and part of that, that will automatically lead to a loss of unitarity because of the gravitational field of the various bits and pieces of your apparatus.
In black holes, one distinction that's often overlooked is the difference between information loss and degrees of freedom.
Degrees of freedom really just means the number of parameters you need to describe a system. You can imagine a situation in which the information completely comes back. So in principle, you could use that information to reconstruct the original state. So you could say all the Hawking radiation which comes out of your black hole is somehow reflected back with some strange kind of mirrors or something like that. And you can use all this to reconstruct the initial state. Well, that would be no loss of information. All the information in the original state can be retrieved, perhaps only in principle, but in principle you could retrieve it later on. Now that's different from degrees of freedom. It's almost the same, but it's different because in degrees of freedom, you might have a complete randomness about it. It may be that the dynamics is not determined, and you just have the same, they happen to be the same number of degrees of freedom afterwards as before, but they're nothing really to do with the ones you had before, and they are completely randomly determined. So they're not the same. What I would argue for was there is no reason to believe the degrees of freedom are preserved, and therefore there's no reason to believe that information is preserved.
So in 1999, Juan Maldacena published a paper on the ADS CFT correspondence, which is just a conjecture, of course, and it's not been proven whatsoever. But essentially what that is you've got quantum gravity, which is equivalent to CFT, a conformal field theory, which is dependent on unitarity. So therefore, quantum gravity is dependent on unitarity. And I think that was probably the key to why Stephen made this spectacular U-turn at GR17.
ADS-CFT seems to be a strange place to go for confirmation of unitarity. I mean, I think Stephen, well, one can quite understand that he was really wanting to get the answer to deep questions and realizing that he himself was had a serious disability and his life might be cut short at any time. And so I think he more or less was too tempted to grab onto theories which maybe had a chance. And I'm afraid that ADS-CFT, I wouldn't even say it had a chance.
The ADS-CFT ideas are still conjecture. I mean, you're stating that, quantum gravity is equivalent to some conformal field theory, and the conformal field theory is unitary. But the details of that equivalence really matter in terms of being able to make this argument. So, I would assert that the argument has not been made in a, clear, compelling way. I don't mean even proven. What would make it compelling is if one had an explanation of how information is regained. If someone had a nice story on that I could understand and believe, then I'd certainly be happy to change my opinion. I don't have some ideological perspective that there's some grand reason why information must be lost. Information would be lost in the usual semi-classical picture, but I don't believe, the usual semi-classical picture can't be exactly right.
Although most physicists accept information preservation, a spanner was thrown into the works in 2012 when the firewall paradox was revealed. Astronauts falling into a large enough black hole should feel nothing special at the horizon. But information preservation seems to imply they'd be burnt up in a firewall.
These are views which are introduced in order to preserve unitarity in a way. And these get rid of the horizon to a black hole. Now, to me, that's just, you see, the horizon to a black hole, according to my understanding, and certainly the understanding of most people who work on large-scale physics, things to do with general relativity, the surface of a black hole is nothing like, locally, it's just like the rest of space-time. As you fall into the black hole, and you might say you've got a little dial that says, whoops, you've just fallen through the horizon. You say, oh, did I? You wouldn't feel anything. There's nothing special about the horizon. It's a speciality, if you like, as if you work back and look at some global thing which you say, this is where you started to lose information or something. That goes against the grain of general relativity and what general relativity is all about.
Another argument put forward by quantum gravity proponents is that in models inspired from string theory, like the fuzzball paradigm or in loop quantum gravity, information is preserved.
Sure. I mean, there are plenty of things that people say, propose, whatever, but I mean, the fuzzball idea, for example, involves you've got this gravitational collapse, but somehow when it gets really close to Schwarzschild radius, it now tunnels, is the word, into, this fuzzball configuration, which is not a black hole. It's something incredibly close to Schwarzschild radius, but is outside of it. And I mean, maybe wishful thinking is a little polemical and strong, but, I mean, of course, yes, you can kind of count fuzzball states and argue that there might be a high probability of getting to them, but how you would do that dynamically, especially in a collapse where you've got very little time before you're going to form a black hole, and you don't want to do it too early because then you're going to be violating general relativity in a regime where, through neutron stars we can test it. So, I mean, the alternative ideas are much along these lines that, there are proposals out there and, they're not refutable proposals, but they're not kind of deep backed up with, I mean, we don't have a quantum theory of gravity that we can So in fairness to the proponents, I can't expect them to, show me the calculation that proves that the tunneling takes place and explains exactly how it takes place. All they can do is make some plausibility arguments. I mean, in this case, the plausibility arguments don't sound terribly plausible to me.
Whether the singularities inside black holes will resolve themselves by some new theory, okay, maybe they will, but it's not a theory that we need to worry about for a long, long time. Maybe it addresses the black hole so-called information so-called paradox, but I don't regard it as a paradox, because why should information not get lost in the singularity? Unitarity has already gone out the window, in my view.
Whether or not in the end of time, once we really understand quantum gravity or so forth, it turns out that the information is preserved, I believe that that's a possibility. But I don't think that there are any strong arguments at present for that.
This film was shot at the Black Holes Inside and Out conference in Copenhagen, and we have several upcoming films with many more experts who reveal the cutting edge in black hole research. So stay subscribed and find the link to our black hole playlist in the description below.